Welcome, everybody. I think everybody knows who I am, but in case you don't, I'm Dr. Beachy. I'm the department head, and when I took this job 4 years ago, my wife said, "Aren't you excited? You get to have graduate students." And I said, "I never wanted any graduate students. I already have 2 children." So anyway, the only reason I ever thought I should take on graduate students is just because I got to keep up with these other sons of bitches that are working so hard and taking on graduate students. So I figured I'd better fit the role model. So, despite that, I didn't want graduate students, and the first 2 that show up turn out to be 2 of the most interesting people I've ever met. And everybody here completely agrees, apparently. So this is round 1 of those 2. This is James. I have a little bit of story to tell about James. I don't want that yet. I'll take care of that. James got, he went to community college at Laramie County Community College, graduated from there in 2013 with an associate's degree. Went to the University of Wyoming, graduated with a BS in zoology in 2015, and began here in the fall of 2015. At this point, if you look at his vita, he's already got a publication. He has 3 manuscripts in review. He has made, in his young career, 23 presentations at scientific meetings. He's an active member in 10 scientific societies. That's a good start. I dig that. But when I first ever saw James, it was in his role as drummer for the band Nirvana. At some point during they exploded onto the scene when they appeared on Saturday Night Live. It was the first time I saw Nirvana and James. And that was when they played Smells Like Teen Spirit. And I thought rock and roll was about dead, but they saved rock and roll. So for that, thank you, James, and thank you, Kurt Cobain. But unfortunately, Kurt Cobain struggled with life, suffered from depression and too much drug use, and committed suicide. That caused Dave, to decide to take stock of things and his life. And during that time, he decided, well, let's give college a try. And there he is there. So at that point, he decided, I'm going to change my name from Dave to James. And that's who we have now, is James. After a few missteps while in college, he discovered other paths to take during the college career, which included trying to become a naturalist. As many of us know, one of the perks that comes with being a naturalist is the cool gear that goes with being a naturalist, and no one has more gear than James Erdmann. Those of you who have been in the field with James, he has everything in a pocket. If you need it, it will come out of his pocket. He has everything. For example, the famous spork. Almost everywhere you go, James will have his spork. Now, this is not something that was rehearsed. Do you have your spork right now? He has his spork. Everywhere you go, if you end up in a restaurant, including a very nice restaurant, the spork will come out. I don't get it. That's one of his favorite pieces of equipment. He always has it. Another piece of field equipment that naturalists have is that little handyman that has pliers and a screwdriver. And that gives me a favorite story of mine, the one that my family likes best. Those of you who have been to my home and have had many beverages have seen that I have a bottle opener mounted on the side of one of the cabinets in the cabana kitchen. I love that bottle opener. So I was really distraught when I was cooking dinner during a graduate student dinner night, and James walks into the kitchen, and that bottle opener with all the screws is in his hand, and he says, "Where do you want me to put this?" And I was like, "Oh, it came down. I'm so bummed. Just put it there on the counter." And he says, "Oh, it didn't come down. I took it down. That's not a good spot." And he did that because he had his handyman. And I shook my head, and I just said, "I want you to put it back where it was." And he just looked at me and said, "Whatever." And he put it back. So it's still there, and it still works really well. For my family, that created the opportunity to have an expression for James. Hyla and Wyatt love to say, "Oh, that's so James." So whenever we do things that have sort of that nature to them, they love to say, "That is so James." So he's made an impact on my family, at least. Another place he's had an impact is in the museum. I spoke with Kyle. Kyle wasn't able to make it today. He's on vacation with his family in Wisconsin. However, I said, Kyle, tell me about James in the museum. And Kyle Pillar, who you may not have noticed, is kind of a gruff guy. He's kind of a curmudgeon, and he's really picky. And if you haven't noticed that, he is. Anyways, so I said, tell me about James in the museum, and Kyle actually began gushing a little bit. And he talked so much about how positive James has been for the museum. 3 things. He talks about the fact that James lives there. Kyle likes that. James is really good at outreach, and that's really good for our museum. James has learned a really hard set of software called Specify. It's required if you're going to work in a museum, and that's been one of his good skill sets as he hopefully continues to get to use Specify in maybe his next job. His most remarkable thing is that he's always got an army of volunteers in that museum. If you go in that museum and if there's people in there, chances are it's more than one person. It's 3, 4, 5 people, and most of those people tend to be volunteers that James has been able to recruit. And some of those volunteers have literally changed their major to biology because of that experience. So that's pretty cool. James is about as serious about the activity of being a scientist as you could imagine in a graduate student. Here he is here showing me about all the stuff that he knows how to do on R. James is highly proficient in R, which is what all the cool kids do nowadays, and all of us need to catch up at some point. It's an excellent skill set I don't have. I'd like to learn it. James has also been the president of the BGSO, and one of the cool things they did was to build this great big phylogeny out on the quad on Darwin Day. I'm hoping that you first-year graduate students and undergrads will continue that tradition of building that tree and maybe doing one step further with that tree in next year's Darwin Day. Now, James isn't just all work. James has done very well at assimilating to South Louisiana. And as you can see here, he's very serious about it. But that's not his best example of assimilation and enjoying himself. Here is James at this year's Mardi Gras, to which he's clearly assimilated. And I'm really excited about what James has to say and share with all of you today. So I want to present to you the ugliest girl I know, James Erdmann.
Thanks for the introduction, Beachy. I do have to add a couple things. You can look at my birth certificate. I've never been Dave. And then also, you did tell me one day that that bottle opener was in an inconvenient spot because it's really low, and you had to sort of, when you went to open it, you spilt some of the drink sometimes. So
Fair enough.
that wasn't completely unprovoked. All right. So I'm going to tell you guys about the projects that I've been working on the past couple years for my thesis, which is about the function of toe movements in feeding with the Gulf Coast toad. And before that, I want to tell you a little bit about how this project came to be. So I guess before I was a rock star, I was also a fairly young naturalist. I love to spend a lot of time out on streams and in ponds, catching all those riparian critters. And I would even occasionally get in trouble doing that, such as this case when I'm out looking for stuff while I'm in a nice suit at a wedding. But I think I may have gotten in trouble for getting really muddy. And I would often catch frogs, toads, things like that, and bring them into my house. If I could convince my parents, sometimes I didn't need to convince them, I'd sneak them in a pocket. And I would have them in these nice terraria where I would observe them and watch them eat and watch them just see what an animal does. So I was interested in behavior from a young age. And then when I came to graduate school, I had spent some time thinking about what I wanted to work on. And this guy here, Beachy, who just introduced me, he picks me up when I came to visit from the airport in June of 2015. And we're in the car and we're talking about, sort of just life and introducing ourselves. And he asked me at one point, what do you want to work on? And I had spent some time thinking about this. And one of the things that I was interested in is, from my childhood, is when I would catch the things like toads, I would watch them feed, and I would often see this really weird behavior. You can see here where this toe is wiggling. It's got this strange vibration to it while he's staring down some of these crickets. So I told him about this idea, about this weird behavior, and don't really seem to know why any amphibians do it. And so I did all the literature searching, and told him about some of the theory as why they may or may not be doing it. And eventually he says, "Oh, okay, that sounds interesting. Go for it." Or at least that's my interpretation of what he said. And so that's what I did. That's what I built my project around. Is this question of do these toe movements serve a purpose in feeding? So is this toe vibration doing something for the toad that helps them catch prey? And to see how you would find that out, turns out that somebody else has asked this question before. In 2008, Hagman and Shine in Australia published this paper looking at cane toads. And you can see cane toads right here doing it. And they sort of asked the same question, but they had a more directed question of, is this behavior a lure? So is it attracting prey? And what they found was that they tested it on both metamorphs, which are just like baby toads of the same species of cane toads, and then also with crickets. And they found that after a certain time period, so they took this picture at the beginning of the trial and at the end of the trial, and they found that metamorphs, when the toads were wiggling their toes, would approach. They would get closer to the toad, which you can see over here. So the distance goes from higher to lower. So they get closer to the toad. And so they concluded in this study that these toe vibrations are serving as a lure for conspecifics. However, there's a couple issues with this study. One of which is that, at least in their natural habitat in Central and South America, cane toads aren't particularly known for eating other toads or other vertebrates. They mainly eat insects and other arthropods and things like that. And another thing is that they tested it with crickets, but the house crickets that they tested these with also are not. They don't overlap with the native range of cane toads, so it wasn't necessarily a good study insect to test this against. So that sort of leaves the question open still as to whether it actually is a lure or maybe something else. So we have to go back to this question: is it helpful in feeding? But one thing that they didn't test is if there's any reason to begin with to suspect that it's helpful for feeding. And one way they could test that is to see if feeding success is associated with it, to see if toe vibrations, animals that toe vibrate, have a different feeding success than animals that don't. And if it does serve some function in feeding, you would expect that animals that toe vibrate have a higher feeding success than those that don't. And then another thing is what is the actual function of it? What's the mechanism what's the behavioral response in the prey that's causing that if it's not a lure? Well, Hagman and Shine, they sort of uncreatively suggested that there's not really any other thing that it could be from luring. But myself and others have thought that maybe wasn't the whole story, that there might be more to it than that. So it might be a lure, or it might not, but if it's not a lure, that doesn't mean that it's non-functional. It could still serve some function, but in a way that they couldn't explore. So one obvious example of it not being a lure is not being having any function. So that would be just like the toad being excited, and so it's excited that there's prey around, and so it starts vibrating its toes. Just what this is often called a displacement activity. And so this would be the sort of the null where you wouldn't expect it feeding success or anything like that to be associated with the toe vibrations. However, in a sort of a rebuttal paper that came out the same year, the author suggested that toe vibrations might serve as a signal that stimulates prey movement. And since toads are mostly visual hunters, if the toads are doing something that get the prey to move around more, this could also conceivably be doing something to help them catch prey. And sort of the opposite of that, if these toe vibrations are slowing down the prey, and their prey items are maybe something that will hide very easily or moves very quickly, if the toads are toe vibrating and they get the prey to slow down, it would give them more opportunities to actually catch the prey. So this is another conceivable mechanism by which these vibrations may be having a function. But then the question you have to ask from that is how can you tell these things apart? And so I had to develop this framework for actually testing these ideas and build this framework to see how you could explicitly compare and contrast these ideas with how they fit with each other. And so for luring, it would be under the direction of prey movement. So like in that Hagman and Shine study, it would be if the prey are moving closer to the toad or possibly further away. And then the other aspect, like for stimulation and habituation, is if the prey are moving more or less. And so from here we can kind of make this little it's a plot of the behavior patterns. So with the prey quantity, so how much they're moving, they could be moving more, less, or unchanged. And then for the direction, they can be moving towards the predator, towards the stimulus, away from it, or neither towards nor away. And these can be controlled against be compared against a control that we'll talk about. And so within these, we can plot some of those ideas of stimulation and habituation and then luring. So pretty much any time the prey are moving towards the predator, it can be considered a lure. Sort of no matter if they're moving more or less compared to another control condition. There might be different sorts of lures, I guess. And then if prey are moving more, but they're not moving towards the predator, we could call this stimulation. So this would fit under that idea that the toe vibrations are getting the prey to move more, and then that could be the mechanism. And then similarly, if prey get to move less, but they're not going towards the predator, we could say that this is habituation. And then these two right here are sort of the null where we would expect the animal, the prey behaviors to fall if it's none of those three strategies. So sort of if it doesn't cause some sort of behavioral response in the prey. So then you have to ask, how do you measure these? In the Hagman and Shine study, they just took a picture at the beginning of the trial and at the end of the trial, but that won't be sufficient if you want to actually see how much things are moving. So we're going to need video footage. And then one of the other things I wanted to look at was seeing how different substrates play a role. Because if we look at that system of the prey manipulation strategy is what I call them, what's going on is that the toe vibration is serving as a signal that the prey are perceiving, and in theory, if that signal is being transferred on something that absorbs that signal, whether it's vibrational through the substrate or acoustic, it would be less likely that would have an influence on their behavior. Whereas if it was on something that was really sort of noisy, like it's noisy and flat like a paper, you would expect that signal to transfer to the receiver or the prey really well, and so you'd expect a more exaggerated response. So that's something else that I included in my design. So, like I said in my introduction, I use Gulf Coast toads. These guys are pretty sweet toads. They're native to around here. They're super abundant in town. Yeah, they can get really big. They're fairly charismatic toads. They're really pretty. And I fed them woodlice. So these little guys, call them pillbugs, roly-polies. They have lots of names. But they're also very abundant around here. And the reason I chose them as the prey is because they are a known dominant prey item of Gulf Coast toads. And then to analyze the video data that we collected, we use this program called Tracker, which is this nice open source program that lets you quantitatively track the movements in two-dimensional space. So here's what my lab setup looks like. So I have 3 cameras. I have this overhead camera that I use for Tracker, so that I could track the positions of everything. And then I have these 2 cameras on the side looking into the arena. And I use those so that I could actually see the toad movements, because if you just looked overhead, the toads are kind of fat, and a lot of times you wouldn't be able to see the toes. It would sort of be covered over. So that's why I use these 2 side cameras. And then I also set up this little kind of hangman jerry-rig thing where this pulley system, so that I could turn on all the cameras and put the toad and the woodlice in these little containers to keep them separated until I started my trial. And then I would lift those cups after I started my cameras and then let the trial commence. So we'll look at sort of what one of those theoretical trials how it would play out. So over here, the start of the trial, the end of the trial. So in terms of the prey, if the toad eats the prey, so those little chomps, those are every time one of the 5 woodlice get eaten. So in this example, all 5 would be eaten. So by the time it gets to this one, there's no more woodlice left in that trial. And then down here is looking at the toe vibration. So say at this point is when the toe vibration starts. So they don't do it continuously, like as soon as they see a prey item or like just always. It seems to happen in response to feeding and seeing prey. And so that's also one of the reasons why it was worth looking into. So for the comparing the movements, I talked about controls, and I have 2 of them. So I want to look at the behavior of the woodlice during the control or during the toe vibration period to see how they're behaving. And to compare those with controls, I used a random time before the toe vibration started during the trial, and also 5 seconds before to help account for some of the temporal variability and sort of to constrain any changes that might be happening in between there that are more long-term. But responses might not be instantaneous. There might be a delay. So I wanted to look at a few different time points to see if there's a behavioral response in the woodlice when it's actually occurring. So I also sampled a half a second after, 1 second after, 2 seconds, or 1.5, 2 seconds, and then 5 seconds later. And so I have a total of 18 sampling points, 6 from each of the 3 periods. So during toe vibration, 5 seconds after, or 5 seconds before, and then a random time before. But if you notice, if we want to look at toe vibration, these 3 all got eaten before toe vibration ever occurred. So we're restricted to only using these 2 woodlice. So we're going to look at, in this example trial, we can only look at these 2 in terms of what they're doing during toe vibration and then before. So up here is how we're going to look at feeding success. We're going to look at how many prey they eat and then how fast each prey item gets eaten. And then to measure the mechanism or the manipulation strategy, we're going to measure compare those three time periods against one another. And so once we've done the trial and put everything in the tracker, and we've got X and Y coordinates for everything, this is what one of those looks like. So right here is all these 5 points are the woodlice. So the cups have just been lifted and now they are exposed to each other. And there's a toad. I have 2 points on them so we can track their orientation. And this is a very exciting thing of what one of the trials would look like. So I got a whole bunch of those. So it was more than just watching the toads and seeing how many prey they ate and trying to qualitatively assess what was going on. It was rather quantitative. So I used those 7 objects, the 5 prey, and then 2 on the toad, with an average of 600 data points. So there was an average of 5 minutes per feeding trial, and a sampling point every half a second. And then ended up with 90 trials, and so that brings us to 382,000 lines of data that we have to work with. But those are only the time and the X and Y position of everything. So to look at the direction and movement, the amount of movement, we had to do a little bit more work. So I had to develop these formulae for the velocity, which is just typical Pythagorean theorem to get the change in position. So that's the hypotenuse of the direction, and then divided that by the change in time. And then acceleration is just the change in velocity over time. And then for direction, it's the change in position of the toad, or of a woodlouse, with respect to a constant position of the toad, to control for the movement of the toad. So these are how I actually got the movement data. So now we can look at what I found. So in total, I got 91 trials. I used 32 unique animals for these. And out of those 32, a whole 8 of them had at least one trial where they toe vibrated. And so I ended up with 11 trials where the animal toe vibrated at some point during the feeding trial. And interestingly, a lot of the times where an animal would toe vibrate once, it would do it more than once. And there was always at least also one trial where it didn't toe vibrate. So it's not this like definitive like yes or no kind of behavior. It sometimes happens, sometimes it doesn't. So we can start to look at feeding success. So here's the animals that did not toe vibrate, and here's animals that did toe vibrate. And then over here is the number of prey items consumed. So if you look at this, the animals that did not toe vibrate consumed on average about 2.5 woodlice, whereas animals that did toe vibrate consumed on average over 4.5. So that's a difference of over 4, and that is statistically different. So that's an interesting finding. But then if we go back and look at those single individuals where the animals had a trial where they did toe vibrate, and compare that with a trial where they did not toe vibrate, they also consistently ate more. So it definitely seems like animals that toe vibrate are eating more woodlice than animals that are not. And I talked about the substrate, and there's also a substrate effect where animals on soil ate more woodlice than animals on paper. This is sort of counterintuitive to what we would have expected if the toe vibrations were having an effect, or any effect in general was going on with with the toads because because we would expect that paper would have sort of exaggerated any sort of responses in the woodlice that could have benefited the toad, but it doesn't seem to be the case. And they're different. Now we can look at how quickly the prey were eaten. So these are the prey number 1 through 5. The gray bars are the animals that did not toe vibrate. The white bars are the animals that did. And then this is just how many seconds it took to eat those prey items. And there were not any differences among these. So animals that toe vibrated did not eat their prey any faster than animals that did not. But they did eat more. And then looking at how the substrate played a role, interestingly enough, there was an effect of paper, of substrate where animals on paper ate slower than animals on soil. So not only at least for the third prey item and the fourth prey item as well. So toads that were on soil ate woodlice, eat the third and fourth woodlice faster than toads that were feeding on paper substrate. So to summarize the feeding success stuff, toads that toe vibrate definitely seem to eat more prey than toads that do not toe vibrate, but they don't eat them any faster. And then also interestingly, toads that eat while they're on paper eat less prey than toads that are on soil, and then toads that are on soil also eat at least some of the prey seemingly faster than those that are on paper. So now, that's all we're going to talk about for the feeding success stuff. We'll go to the movement results. So from these, I looked at the direction and position, or the amount of movement for each of these. So here we've got increasing, decreasing, or 0 for the acceleration. Over here is direction, towards, away, or neither. And so we get these counts for each animal and for each woodlouse in terms of what they're doing during these 3 points across those 6 intervals that we talked about. But this isn't fun to talk about. Not very fun to look at, I guess. So the way I'm going to talk about this stuff is through triangle plots or ternary plots. It's a 2-dimensional system to represent 3 dimensions of codependent data. So it's typically proportionally scaled things. And geologists use this a lot to classify different amounts of for the different classifications of particles, for example, in soil. And then in this case, it's just showing you how to read this in terms of the relative percentages of silver, gold, and copper on how that's going to influence the color of the metal. So down here, in this case, it would be when it's 100% copper. Up here is 100% gold, and it goes down to this line right here, which is going to be the opposite of the point, and that's going to all be 0%. Then similarly from silver, it's going to go from 100% silver out to 0% silver. So that's just how you read those, and I'll go through that a little bit more. But if you pick out any point on here, it's always going to sum up to 100%. And then when we look at this, when we're thinking about this stuff, if we compare across these 3 sampling periods against co-vibration with the 2 controls, our null hypothesis is that there's not going to be any differences in the amount of movement for acceleration or direction. So to look at these again real quickly, so we have here's the toe vibration period, here's 5 seconds before, and then the random time before, and we're only going to have these 2 woodlice in this case to work with. And like I mentioned before, I had a total of 11 trials where the animals toe vibrated, and coincidentally I had 11 woodlice that were present during a toe vibration period that all these movement data are based on. So let's get into it. So The light circle is going to be the random time before. The middle, I guess, middle colored diamond is going to be 5 seconds before, and then the green triangle, the darker triangle, is going to be during toe vibration. And so this is looking at acceleration, and so it's going to be the percent of animals that are slowing down, the percent of animals that are speeding up, and then the percent of animals that have an acceleration of 0. So that either means that they're not moving, or that if they are moving, they're moving at a constant speed. And the circles around these are sort of to indicate whether the values, those single points, are significantly different from one another. So if we look at this case, toe vibration right here does not overlap. The circle around that does not overlap with the circle around the random time. So that shows that animals during toe vibration have proportionally more of a zero velocity or zero acceleration than animals during the random time before toe vibration occurs. And this is looking at a half a second after. So mostly for the sake of time, I'm only going to present 3 out of 3 sets of these data. I'm going to talk about half second after, 1 second after, and then 2 seconds after. So to show this again, 5 seconds before is not any different than toe vibration, but this because animals are either more animals have a constant acceleration, which would be evidence against stimulation because animals are going away from increasing. So those animals are not speeding up compared to the random time at least. Then looking 1 second after, there are proportionally more animals decreasing, so slowing down during toe vibration as compared to the 2 random points. So you can see that the general trend is more proportionally more decreasing, but also proportionally fewer increasing. So there's more prey slowing down, and this would be evidence for the idea of habituation, where the animals are slowing down and then fewer of them are speeding up. And then also during toe vibration, it's different from both of the control periods. And then 2 seconds after, there are not any differences between the 3 groups. So I would have to look at this in more detail, but it might indicate that the animals have either sort of all stopped and are just sort of doing what they were doing before, or starting to return to their normal behaviors by this point. But yeah, it would just, this alone, after 2 seconds, would indicate that the woodlice are not having any response to the toe vibrations. And then looking at the direction stuff, a half second after, there are more prey that are, or fewer prey that are moving away compared to the random time before. So, but not compared to the 5 seconds before. So this may be evidence against lure, because if you look down here, so there's fewer prey moving away, which means that there's going to be proportionally more prey moving neither towards nor away, and then also slightly, mostly moving neither towards nor away, but also a slight increase in the amount moving towards. And then 1 second after, there were no differences between the groups. So this would sort of just be evidence for the null, where the prey are not having any sort of behavioral response. They're not moving away more or towards any more than the control times. And then 2 seconds after, however, looking at direction, there are proportionally very few prey moving away compared to the control times. So it looks about the same as the first one, but it's different. It's different from both of the control times. And so this would sort of be evidence against the deterrent. So very few prey moving away, and more prey going towards, neither moving towards nor away. And this might just be because the prey by this point are stopped, and if you're not moving, you can't move towards or away from something. So to summarize this stuff up really quickly, between a half second before and 2 seconds after, or between a half second after toe vibration started and 2 seconds after, which represents 4 sampling times, there are 3 cases for acceleration that the toe vibration time was different from either one or both of those control periods, and in this case they're either decreasing, so they're slowing down, or having more of a constant acceleration. So which means they're either moving the same rate or had stopped by that point. And then for direction, there were also three periods during this 4 sampling times where the toe vibration sampling was different from either one or both of the controls. And this turns out to be fewer prey moving away, and then more prey were mostly moving either towards nor away, which would also sort of support that the prey had stopped, or that some of the prey were moving towards the predators. So in a second we'll look at how that plays into our design of the template of those different behaviors. And then one of the important things, at least for the ones I showed, is that the control points were never different from each other. So this sort of helps to validate that this is an appropriate way that you can look at this behavior, and that it might be important to use multiple control points. So if we put this all together, toads that toe vibrate have a higher feeding success than those that do not, which is pretty interesting. And then toe vibrations seem to have a dampening effect on woodlice movements compared to controls. And this fits into one of 2 possible prey manipulation strategies. Seems to be more evidence towards habituation, but also might be this odd form of luring. So if we look back at that this thing, we can start to reject some hypotheses. So if we look at first going to look at the amount of prey movement, there were definitely not more prey moving away. So we can cross all that out, which means that stimulation is already off the table. And then similarly, there was definitely a change in the amount of prey movement, but it was towards prey moving less. So we can also cross out the lack of change. And then the prey were also pretty consistently not moving away. So we can cross that out. And so what we're left with is one of these 2 descriptions of the prey manipulation strategy of toe vibrations on woodlice. So we're going to conclude this up. Toe vibrations do seem to play a role in prey acquisition. It seems like it's, at least from the data that I've collected and presented, it seems like toe vibrations do play a role. They have a function in prey capturing by slowing the prey down, this habituation, or possibly this odd luring strategy. And then another really interesting thing is that this is the first study that's tried to quantitatively look at separating these manipulation strategies. So a lot of times when people suspect that the animal is doing some behavior that's a lure, it's just like anecdotal and it never gets tested. Sometimes it does, but almost never, well actually never as far as I know, has anybody ever tried to develop a framework that can actually separate between these different strategies. And in fact, for prey habituation, very little has been developed on that. And so this hasn't really been integrated into like an overall model before to see actually quantitatively how predator behaviors are influencing their prey. So I think that's pretty cool. But this is a complex behavior, so I only looked at it in one predatory species, the Gulf Coast toad, and only one prey species, woodlice. And even though woodlice make up a large part of the toad's diet, that's not all they eat. So it might be that toad vibrations are do more clearly serve as a lure in predatory prey species like a spider or a ground beetle. Or toad vibrations have also been seen by me, at least in Gulf Coast toads, happening during amplexus, both in males and in females, which might suggest that it is just maybe an excitatory response, that maybe it doesn't have a function. And it's also been seen, it's also known as a general behavior in male territorial displays across some species. I don't think Gulf Coast toads do it, but so it is this behavior that's not very clear cut in terms of what it actually does. And this study by no means is like the end all be all on that. There's still a lot of stuff that's little unanswered questions still, but I think it's a really, really interesting thing that we've looked at, and definitely something that is worth looking at a little bit more. So with that, I have a lot of people to thank, really good committee members. Beachy has been incredibly supportive. Brian Crowther, I wanted to put Brain Crowther, Dave Seaver and Sonny Fonno, they're all great help, giving me good feedback on everything. Anthony Baldini is right there, and Kaylin Novak put in a lot of hours staring at videos and processing everything and helping me take care of the toads. So I am very grateful for all the help that they've given me. I have a lot of other people to thank. Schaefer helped develop my conceptual framework on how to statistically compare the movement data, and a lot of you grad students have been very helpful in terms of just your camaraderie, so I really appreciate that. Got a scholarship, at least Oakland Memorial Scholarship, to help buy some of the camera equipment, and then Beachy has funded my toad's food. So last people I want to thank is you guys for your attention and presence, so thanks. I'm happy to take questions. Sure.
Well, congratulations on questioning the creativity of Agnew. Is there a literature for this excitatory behavior? I think about my cat, after a bird, tail's going.
Yeah. So yeah, it's I think Nico Tinbergen sort of developed the theory behind that, which is called the displacement activity, which is when an animal does this behavior that's like, at least doesn't seem to be related to the task at hand in any way, and we're not really sure why that happens. It's probably like just this like some sort of neuronal thing going on where there's so much action potentials that it's might be jumping across neurons, and so there's other behaviors that are going on. But no, it hasn't been studied much. Yeah, no.
The challenge with the paper versus the soil. Do you think that maybe it could be a possibility that the toad could be being disturbed or distracted by the sound of the paper, like when it's moving around on the paper, or the transmitter around the paper? That might be the reason why they're eating less.
Yeah, that's definitely possible. But I guess in retrospect, when I was reading up on it more, the substrate does definitely have an influence on both woodlice behavior and on toad behavior. So since these guys are kept on soil, both the woodlice and the toads, when they're introduced into this unfamiliar, like really dry, really barren substrate, they're probably going to be a little bit more stressed out than they would otherwise. And so I think that might be a big part of why there was different feeding success. Okay. Oh, yeah. So in my cases where an animal toe vibrated, it had always eaten at least a few of the prey items. So it actually, in most of the cases, and this is why there were 11, I had 11 data points for that last set of movement data, was that a lot of the cases, the toads would have actually eaten all of the prey, and then they would start doing it, which is kind of odd behavior. So, yeah, they always ate at least some before they started doing it. They would never start toe vibrating before they start eating. Any others? Anthony. It's possible. So I actually do have some data on that. I guess I can. I don't think I have that specific figure, but toe vibration actually only occurred in females or animals that I couldn't identify, which were probably females. There weren't any trials where it occurred in a definitive male or in what I classify as a juvenile, so a smaller toad. So it is possible that it's like a developmental thing that maybe either it's like sort of onset by a change in the feeding strategy, or maybe it's something that they observe, which is it's not out of the realm of possibilities. But yeah, it's from what I've seen, there is an age class effect, but some other studies have not seen that.
So I'm really enjoying this video that you've been watching it. And I know that you did say that maybe if it were a different prey, even though this is the most common prey item, and I remember when you first started talking about doing this, and you were talking about maybe using crickets or something like that. So I wonder if that would make a difference, especially when you think about maybe the luring idea. Because at least watching this video, it's not like he needs to lure these guys, and it's not like he needs to transfix these guys, because they're just kind of sitting there, and if he wants to eat them, he'll eat them.
Yeah.
So do you think that that's maybe, I don't know, do they ever do more than one toe at once? Because sometimes he turned away and had the toe that you couldn't even see twitching.
Yeah, so when they do it, they usually do both toes.
Okay, so then he is showing him that I can see.
And yeah, so it might be because the way I have this set up, like I couldn't have tested this, but it's reasonable to think that maybe that it does still have some sort of habituation effect in these guys, because since these guys are really fossorial, maybe they would normally just duck for cover if they noticed that the toad was hopping around.
And so in the soil they had the opportunity to eat it.
No, I didn't see it at least. Just because I did try to pack it down, so I would make sure that they wouldn't just because when I would lift those things, like if in that funny video that I showed, they would like pretty much immediately start running around, like trying to find somewhere to hide.
So watching the video, I noticed that the toad was kind of wiggle its toe a little. So what would you classify as like an official wiggle? Was it just like one little up and down move, but then you have to flutter it for a little while, or they just need the toe trying to balance itself out and be skating for a little?
So in terms of the categorical classification for feeding success, if they just had one off, like little toe vibration, maybe they were just adjusting their foot or something, we probably wouldn't have picked that up. So when they do it, it's fairly conspicuous, at least at some point. And then for the movement stuff that I looked at, the prey would the toads would toe vibrate, and that's what that little square, that gray square, was, because they would do it for some period. They wouldn't just do it once and then do it. Yeah, so that's why I felt comfortable like with that, doing the multiple time samplings, because they were still toe vibrating during that time. I collected most of them in Ponchatoula, or near Ponchatoula, at Friends Pond, but also a lot from around Hammond, some from North Oak Park, a couple from down from 51. But yeah, all local. You have a follow-up thought?
But, no.
Okay. Yeah, Sean.
Dave, what's the sensory modality here? Are the tool bugs, they're able to see the toes moving? Are we sure? Is there a vibration that could be going through the substrate?
So I think the most likely thing that's going on is that they're picking up on the vibrational signal that's transferred through the substrate, because pretty much all animals, a lot of arthropods, even vertebrates like toads, especially frogs and toads, they have a really high sensitivity to substrate movements. So I think that would be the most likely source of perception in the woodlice. But it's possible that it is a visual signal or acoustic. And there were some trials where I could actually hear the toad tapping. Yeah, sure. Yes. I don't know. Seemed like a good number, I guess. So I would starve the toads for about 2 weeks before I did my trials, and I picked 5 just to have like a consistent number, and it kind of seemed surprisingly to work out, because a lot of the times I would eat all 5, but a lot of times I wouldn't eat all 5. So yeah, it just kind of seemed, I guess, like a decent number. There have been some other studies comparing like the amount that they eat, and there are effects of like eating more prey on their drive to feed. So that was also something to take into consideration. So I didn't want to give them like 30 woodlice. Also, I would have run out after a couple trials.
Okay, I'm going to stop it there. James still has his committee defense to go, so let's thank him for his time. Thank
Thanks. Thanks.
I didn't want to embarrass you. I was going to ask this question. You called the toads sweet. How did you prepare them? Did you just eat them raw, or did you put them
Well, you
in
have
a
to be
soup?
careful. You have to cut off those poisonous glands.
Well done.
You did good. Thanks. On this next thing. There's been talk of 2 to 3 hours.
We'll see. Okay. Thanks for watching.